This is the first in a series of videos in which we're looking at solutions to questions from the physics exam of 2024, which of course was earlier today. All right, so let's begin by looking at question 1. Now, question 1 part A shows two lenses, lens A and lens B, and they basically want us to identify the types of lenses shown in figure 1. So we should be able to identify these type of lenses. The first one, of course, is thicker at the ends and thinner in the middle, which of course means that lens A is what we call a diverging lens. So lens A is a diverging lens. If you prefer the word concave, then that would work as well. So this is a concave lens, whereas lens B, which is thicker in the middle and thicker at the ends, that of course is a converging lens, right? A converging lens, or if you prefer the word convex, then either would suffice. So that should have been an easy 2 marks, right? So students should not have struggled to identify the types of lenses because that would have been something that they would have learned, right? All right, let's move on to part B of the question. Part B of the question says a student used the apparatus shown in figure 2 to determine the focal length of a lens. She adjusted the position of the lens and screen to obtain a sharp image on the screen. She measured the image distance V, deduced the magnification M of the object, and recorded her results in table 1 below. All right? So we see the setup of the equipment here. So here we have the object, the light bulb source. We have the object, looks like a grid. And of course, here we have the lens, and of course, the portion of the screen. And of course, the image distance is of course the distance between the lens and the screen. And naturally, they'll be adjusted to actually obtain a sharp image, right? So let's look at the table. In the table, we have the image distance in centimeters. So we have V in centimeters, and we have the magnification M, which is a pure number. It has no units. Now we see the image distances are varied in 10 centimeter increments between 20 and 8 inclusive. And of course, the corresponding magnifications are given in the table as well. Now, what is required of us? We're required to use a scale of 2 centimeter to represent 0.50 on the y-axis and to plot a graph of magnification M against image distance V on the grid provided on page 7. All right, so let's pull up our graph paper and we'll proceed to plotting our graph, right? All right, so let's see, do I have enough space there? A bit less space. Yeah, that should be enough space. Let me just zoom out a little bit. 90%, 90%. All right, so let's proceed to plotting our graph, right? Right, so there we have our axes being drawn. And of course, let's proceed to label our axes. And of course, before that, let's put in our title. So this, of course, is going to be a graph of magnification versus image distance. So we can put in our title, say graph of magnification. Let's put M versus V, right? So the graph of magnification versus image distance. Let's write this better. So graph of magnification M versus image distance V. All right, so that naturally tells us that magnification is going to go on the vertical axis, and of course, image distance is going to go on the horizontal or the x-axis. So here we have magnification M, which doesn't have any units, And here we have the image distance V in centimeters. Now we're specifically told what scale to use for the vertical axis or the y-axis. We're told to use a scale of 2 cm to represent 0.50. So basically means that every 2 centimeter we're going to label with 0.5 increments. So that will be first 2, next 2, next 2 there, next one there, next there, next right there, right there, right there, right there, right there, right there. All right, so let's see what this goes up to. So it starts at point. All right, so 2 cm represents 0.50 on the y-axis. So all right, so this will be 0.50. Where's my cursor? Just like so, 0.50 is a different color. This one not so clear. So 0.50. Then we have 1.00, 1.50, 2.00, 2.50, 3.00, 3.50, 4.00, 4.50, 5.00. I guess we could stop there, right? So our table, our values in the table go up to 3.52. We've gone up to as far as 5.00. Now, we need to choose a scale for the image distance V, which is going to be more straightforward because these values increase in 10 centimeter increments and starting with 20. So we're going to start the axis, of course, at the origin. So this is going to be 0. And then, of course, let's see now, could this be 20, 40, 60, 80, 100, 120, 140, 160? Do we have enough? Oh, it's actually 20, 30, 40, 50, 60, 80. All right, so using a scale of every 2 centimeters represent 10, 2 to 10. So this would be 10, 20, 30, 40, 50, 60, 70, 80, and of course, all the way at the end, of course, would be 90. Let me just squeeze in that value there. So this would be 90. And of course, our axis V in centimeters. All right. So do we as our graph of a title? Yes, we have a title. Our axes are labeled with quantity and unit. And of course, we can actually state our scale somewhere on the graph paper. Let's see. Let me see. How are these values changing? All right, so we see that larger is going to be something like this. So we'll put our scale here. For the x-axis, we say that we have 2 centimeter represents 10 centimeter. And for the y-axis, we have 2 cm to represent, what's it? 0.50. 0.50 units. It has no unit. All right. So let's proceed now to plotting a graph. When v equals 20, m is equal to 0.15. Now, for the y-axis, we chose a scale of every 2 centimeters to be equal to 0.50. What this basically means is that we have 10 small blocks. So we have 10 small blocks representing 0.5. And if we divide that by 10, it means that one small block would be equal to 0.05 units, right? So we have to do something like that in order to locate our values properly, right? So when v equals 20, then m is equal to 0.15. So that means if one small block is 0.05, then we need 3 small blocks. And so we're going to start at 20, and we're going to go, let me see now, where's this thing now? We'll go, going to be, oh, but now let's see this. This one, all right, so 20, this looks like 1, 2, 3, right here. All right. Then, of course, we have now 30.65. So 30, this is the 0.5, 0.55, 0.6, 0.65 right here. Then, of course, we have 40, 1.20. So 40, 1.2, this is 1, 1.05, 1.1, 1.5, 1.20 right here. Right? Then, of course, continuing, we have 50, 1.85. So this is 50. This would be 1.5. This would be 1.75. And 2 small blocks above that, that would write 1.85. Right. Then, of course, we have 60, 2.35. So this is 60. and we go all the way up to 2. This will be 2.25 in the middle, then 1, 2 small blocks above that, so 2.35, right? And our second to last pair of points, we have 70, 2.95. So 70, 2.95, yeah, 70, 2.95. So this will be 2.5, 2.75, 2.95, one small block below 3. So that is right there. And then lastly, our last pair of values, we have 80, 3.52. So this is the 3, 3.5. On this axis, or on this scale rather, we're not going to be able to plot 3.52 accurately. So we have to just make it a little bit close to 3.50. And essentially, those are our points, right? So those are our points, and we can see that obviously it's going to be a nice straight line, but it's not going to pass through the origin, right? So that's fine. So now let's basically draw our line of best fit. So let's draw our line of best fit here. Let me see now. Let me see how I do this. So let's see line of best fit. Looks like a decent line of best fit, yes. So that's the line of best fit there. Adjust it a little. All right, so there we have our line of best fit. And what else are we required to do now? We're required to calculate the gradient. Now, to facilitate this, let's zoom in a little bit. All right. And let's calculate our gradient. Let's try to find 2 points on the line that we can actually use to find our gradient. Um, let me see now. What 2 points should I use? So, all right, I'm going to use this point. Um, let me use this point right here. All right, so that point is middle of 20 and 30. So this point would be 25, and the y coordinate is 1, 2, 3 small blocks above, so that's going to be 0.40. So 25.40. Those are the coordinates of that point right there. And I can use this one right here. It's a nice point. This one is exactly between 70 and 80. So this would be 75, and the y coordinate is exactly between 3.00 and 3.50. So this is 3.25. And of course, we could draw our little triangle, right? So let's draw our triangle. Right, right. All right, so there we have our triangle, right? And of course, we want to calculate our gradient. So let me zoom back out a little bit. Make it 100. All right, so let's go ahead and calculate our gradient, all right? So we can say that our gradient m, or the gradient has given us g. I think it has given us g in the question. All right, so we want to find the gradient g. So we know our gradient formula. Our gradient g is equal to y2 minus y1 over x2 minus x1. So we're going to let the upper point be our x2, y2, and the lower point be our x1, y1. So that means that y2 is 3.25. So this gives us 3.25. So 3.25 minus 0.40. So 3.25 minus 0.40. That's divided by 75 minus 25. Now 3.25 minus 0.40, then that basically gives us that's 2.85. And 2.85, that has no units, and then that is divided by 75 minus 25, which of course is 50. And the unit, of course, for this one will be centimeter, right? So dividing by 50, so that's going to be let me see, dividing by 50 divided by 0.5, same thing as multiplying by 2. That's 5.70 divided by 100. That's 0.057. All the math is correct. So this should be 0.057, and the unit should be per centimeter, right? So let me just check my math a little bit. All right, so that should be it. So 2.85 times 2, that's 6 minus 0.3, that's 5.7, right? So 5.7 divided by 100, that gives us 0.057. That is correct. So our gradient is 0.57, and the unit, of course, is per centimeter, right? That is that there. Now, the next part of the question says, given that gradient G equals 1 over F, calculate the focal length of the lens F. So what we're told is this. The gradient G is equal to 1 over the focal length. And therefore, what this means that the focal length F is equal to 1 over G. And so we see that F is equal to 1 over 0.057, which of course would be the same thing as 50 divided by 2.85. And that's going to give us, where is my calculator? 2.85. That is going to give us 2.85, so 50 divided by 2.85, approximately 17.5 centimeters. So this gives us approximately 17.5 centimeters. So therefore, the focal length of this lens is 17.5 centimeters, right? So that should have been an easy 11 marks. 8 marks are plotting the graph, 3 marks are finding the, well, 11 for finding the focal length, and 8 for plotting the graph, probably about 3 or 4 for finding the gradients. Right. So, all right. So that's that part of the question there. Now let's move on to the next part of the question. Now, the next part of the question says, Figure 4 shows a full-scale diagram of an object O which has a height of 3 centimeters, right? So we're told that this diagram is a full-scale diagram, right? And the height of the object is 3 centimeters. And this object would have been drawn to scale. And of course, if you had been able to take your ruler and measure the height of the object, then you would have seen that the height of the object is actually equal to 3 centimeters, all right? So let's proceed to looking at that part of the question. Now, this part of the question. So let me just clear up my screen a little bit. All right. So what we have here is an object, and of course we have a line representing a diverging lens L. So if you notice, the word diverging is in bold, and of course that means you must pay extra attention to it, right? So figure 4 shows a full-scale diagram of an object O, which has a height of 3 centimeters. Let me just pull it to the center here. All right. All right, so it says, given that the focal length of the lens is 5 centimeters, draw the ray diagram in figure 4 to find the image of the object. So draw the ray diagram in figure 4 to find the image of the object, right? So first of all, we have the length indicated by the letter L, and we're told that the focal length is 5 centimeters. So what this means is that we're going to count 5 centimeters from either end of the lens, and we're going to leave that point X. So this is 1, 2, 3, 4, 5. Let me put that in the color red. So 1, 2, 3, 4, 5. So we put F. Now it is common practice to put the focal length on either side of the lens. So 1, 2, 3, 4, 5. All right. So we normally put 2 positions for the focal, well, not the focal length rather, but the principal focus, right? So we normally put 2 principal foci. So we have one on the left of the lens and the other on the right. So there we have labeled our principal focus, our principal foci, the two positions on either side of the lens, right? Now, what we're told to do is we're supposed to draw the ray diagram to find the image of the object. So what we're going to do is we have to draw a line coming from the top of the object, and it's going to represent the incident ray, which of course is going to be parallel to the principal axis, right? So that's our ray of light coming from the top of the object. Now this line, of course, the horizontal line on which this line right here is, of course, we call it the principal axis, right? So that is our principal axis, PA, right? So the black is not going to show over there. So our principal axis, PA. And of course, we have our focal point or our principal foci, F on either side. Right. So what's going to happen here is this. Now, this light ray is coming parallel to the principal axis. It will be refracted by the diverging lens so that it appears to come from the principal focus. I repeat, when a diverging lens refracts a ray of light that is incident parallel to the principal axis, it diverges in such a way that it appears to come from the principal focus. So before we can actually show the refracted ray, we must use a broken line to show this ray coming from the principal focus, right? So we draw a point from F here, we draw a line going towards that point, right? So that's a straight line. But of course, the straight line should be dotted or broken. So let's just make that line broken, right? Take out some piece of it. That's a big chunk. Right, so there we have our broken line, right? Now let's go back now to extending or all right, so what I should have done is this. Let me fix this a little bit. So this piece is supposed to be broken. Yes, let me take off the entire thing again and draw about the line. I'll draw about the entire line. So the line is coming from the principal focus, comes to this point here. All right, so that's a straight line. Let me continue the line up here. So let's draw it as far as it can possibly go, right? About there, right? So as I said over, the space between the lens and the principal focus must be broken. So let's just take out the chunks of that one there, right? Good. So what this is showing is that this ray of light is actually refracted by the lens so that it actually appears to come from the principal focus, right? Now, we need to locate the position of the image. And for us to locate the position of the image, it basically means that we need to have two rays. So we already drew one ray parallel to the principal axis. And of course, we then draw another ray so that it can actually intersect or appear to intersect the other. So what are we going to do with that second ray? We're going to draw a second ray of light. Let's change the color a little bit, right? Let's change the color. And we're going to draw a second ray of light coming from the same position of the top of the object, right? Let's draw that. And this one we're going to draw so that it passes through the optical center of the lens. So it passes through the optical center of the lens and it therefore goes through undeviated, right? So there we have our two light rays. And what we can see is that this one appears or it crosses the path that this original blue light ray appears to come from. And what this therefore means is that our image will be formed right here. That is right where our image is formed. And because our image is formed right there, we then draw an arrow in the upright direction to represent our image. All right, this line not drawn. All right, so let's draw the position of our image. What color should I use? So let me use black. So we have right here. All right, so that's basically where our image is formed. So we have our image, the arrow. So this is the object O, and this is the image I. Okay. So once again, this is an example of how a diverging lens forms an image. We draw first light ray parallel to the principal axis, and this light ray will be refracted by the lens so that it appears to come from the principal focus. To get the position of the image, what we must do is draw a second light ray, and in this case, we decided to draw a light ray which passes through the optical center of the lens and therefore goes straight through undeviated. Now, this second light ray would intercept the first at the point shown. Of course, it appeared to intercept it because we know that in reality, no light, this blue part of the light is not here, but we just draw it because to show the intended path or the path from which the refracted ray comes from, right? And so therefore, this is where the image is located. So what does it tell us? So say, so given that the focal length of the lens is 5 centimeters, draw the ray diagram on figure 4, find the image of the object. So we managed to locate the image. So that should have been a 4 marks, right? It says record the image distance. So from this diagram, the image is clearly 1, 2, 3 centimeters from the lens. So therefore, this right here is our image distance, right? So that's our image distance, V, and therefore V is equal to 3 centimeters. So the image distance V is equal to 3 centimeters, right? Now, typically, because it is a diverging lens and the image is virtual, and we of course apply the sign convention, real is positive, virtual is negative, because it is a virtual image, we will typically say that the image distance is actually negative. And so in reality, we should write V is equal to minus 3 centimeters. But this diagram actually just shows the distance between I and the line. But if you're going to be quoting the image distance, we should make it negative to actually show that the image is virtual, right? And of course, that answers the next part of the question. The next part of the question says, state whether the image is real or virtual. Now, the image produced by a diverging lens, of course, is always virtual. Diverging lens produces a virtual image. But if we want to show off that, we can also look at properties of the diagram shown, and we can tell that the image is virtual. Now, first of all, let's examine the image. The image, of course, is upright, meaning it's the same orientation as the object. And this is another sign that the image is actually virtual, because you know that real images are inverted, right? So we can say that real images are inverted, and it therefore means that virtual images are upright. So real images are inverted, virtual images are upright. And in this situation, the image is upright and it therefore is virtual. Also, in addition to that, only virtual images are formed on the same side of the lens as the object. Let me repeat that. So because the image is formed on the same side of the lens as the object, then what this means is that the image is virtual. So these are just some properties of virtual images. They are upright, and of course, they're formed on the same side of the lens as the object. And of course, this is the end of question 1 from CSEC Physics 2024.